My name is Dr. Akshay Ranchar, and I'm going to be talking about CFD simulations of aerosols and indoor ventilation to minimize airborne disease transmission. This is part of the virtual workshop by the American Society of Thermal and Fluids Engineering. Airborne droplets and relation to disease transmission is known for a long time that the respiratory droplets carry pathogens. Droplets can be classified as small or large, and the arbitrary cutoff is typically between 5 and 10 micrometers or microns. The difference between the two is that the large droplets tend to settle fast due to gravity, and once they settle on the surfaces, they can transmit through touch. The small droplets can stay airborne for a long time. They do tend to evaporate fast in dry air, but they can transmit pathogens over longer distances. The residue particles after the droplet evaporate are called nuclei or aerosols. So what are the modes of release of these droplets? Talking, exhalation is obviously the first one. It releases around 50 particles per second, and that result in continuous release while you're talking. And the speed of the release can be 1 to 5 meters per second, and a diameter of the droplets is around 10 microns. They can build up over the course of the day. And just to note, the typical ambient airflow around us is somewhere between half a meter to 2 meters per second. Coughing can generate on the order of 1,000 particles at, say, around 10 meters per second and about the same diameter as talking. Sneezing, on the other hand, can generate tens of thousands of particles at a much higher speed, about 20 meters per second, and droplets can be as large as 100 microns. These numbers about speed and diameter are approximate averages, and it varies over a large range. The one thing about sneeze and cough is that the droplets are expelled in a turbulent puff of gas. This keeps them moist for a long time and slows down evaporation, and the droplet lifetime can increase from seconds to minutes. So once they're released, what happens? They travel through the air. So the airflow or ventilation plays a very vital role in disease transmission. It carries droplets between the infected person, the source, and the exhaust where the air leaves the area of concern. The recipient may be somewhere in this path. The droplets do dilute through exchange with the ambient air, and they evaporate depending on speed of gas cloud and airflow and temperature and humidity and all those things. So droplets also settle due to gravity on surfaces that they come in contact with. So what are our typical ventilation options? The most common is the downward ventilation. Here the supply is at or near a ceiling and the outflow is at or near the floor level. The upward ventilation, also called displacement, typically has a low velocity supply from the floor and outlet is near the ceiling. So in this case, the fresher air is closer to the floor where people are, and the contaminated air moves up. The mix of these two would be what we call a tangential ventilation. Here, this air supply is directed at an angle or parallel to floor or ceiling, typically at a higher speed, and this helps in enhancing the mixing in the room by creating recirculation eddies. So which strategy is best? Well, the droplets evaporate, as we said, depending on speed of gas cloud, ventilation, airflow, humidity, all that. And droplets settle based on size and flow conditions. So it's better to choose a strategy that results in travel away from recipients, faster evaporation, and quick settling. That means shorter suspension in air. So which strategy is better is strongly influenced by the specifics of the release and the location of the recipients. So how can CFD help in all this? Well, first, it can help us define the threat. Define particulars of airborne transmission in offices, public transport, malls. Where does it originate? Where does it go? Things of that nature. And can take account the complex dynamics of transmission, airflow patterns, temperature, humidity, all those things we talked about. It can also account for recirculation due to buoyancy and the ventilation system. After the threat is defined, CFD can help us design a control strategy. It can consider various scenarios. We can account for evaporation, settling, breakup during these scenarios, and we can select a ventilation strategy to minimize the potential impact. I'm going to present 3 case studies. First is that of a coughing or somebody coughing or talking in an open room. There's no forced ventilation, just the breeze from the doors and windows. The second is a downward ventilation from the ceiling, as somebody's talking, coughing, or sneezing. And finally, the upward ventilation from the floor, talking, coughing, and sneezing. So this is what happens when somebody is coughing and the cough is expelled horizontally. The room is about 5 by 5 by 4. There's a door and 3 windows, and there's no forced ventilation. So somebody has these coughs 3 times in 1 second, and all these particulars are here. And we consider here 11 droplet sizes between 1 and 100 micrometer range. So as you can see, the droplets spread beyond 2 meters very quickly, and they envelop the potential recipients in this case. Now what happens if the same person coughs 45 degrees downwards? Here what we see is that both the 1 micrometer and the 100 micrometer droplets fall to the ground quickly, and they're not suspended in air for a long time. So obviously this works better in this particular scenario. Now let's see what happens when somebody is just talking, but continuously for about 180 seconds. That's a long time, but not unusual. And there's a small background breeze from the ceiling. And you can see that we are way past the 2 meter in less than 60 seconds, okay? So there is still a danger even in this particular case. Now let's consider the cases 2 and 3, where there is a downward flow from the ceiling or an upward flow from the floor. In both cases, there are 2 outlets. In first case, they are near the floor. In the second case, they are opposite near the outlet, and the particulars are given here. So here, the droplets are transported along the flow path and just showing the standard situation. Now let's consider sudden exhale specification for talking, coughing, and sneezing, which I'm not going to go about. They are summarized here. Now when one is talking, here somebody talks for 30 seconds, takes a break for 30 seconds, and talks again for 30 seconds. In this particular scenario, the droplet spread is very narrow, both for upflow and downflow, and the droplets are transported towards the outer wall or the exit, okay? So not much happens, and the infected person, it does not infect others. Let's take the case of coughing. Here, in the case of the downflow, you see some of the droplets are accumulating near the humans, and then they are first dropped to the floor and then they rise up, the heavier ones. In the case of upflow, as you will notice, they go to the ceiling first, and then they come down to the recipient. In both cases, the recipient, potential recipient, is impacted. Of course, the particular of the two situations are different. And in the second case, it's a little longer time that it takes to reach the recipient. What about sneezing? The final case I'll consider. And here, during the downward ventilation, again, the same thing happens. The most droplets fall to the ground, and some intermediate sizes are suspended and eventually reach the height of the infected person. In the case of the upflow, everything first moves toward the ceiling and then begins to float down and again envelops the person concerned. So in this case, the upflow seems to be a more dangerous situation if you look at just this, but it's very specific to how the situation would develop. So what about so-called social distancing? Different agencies recommend 1 to 2 meters, 6 feet. We can see from the work presented that this recommendation underestimates the impact of exhaled turbulent gas cloud at a high speed. So definitely this social distancing is not valid for sneezing. It's also not valid for talking or coughing, depending on ambient condition, as you have seen. So this recommendation is definitely not valid where airflow causes droplets to travel much further. So what we feel is that recommendation for social distancing should be based on droplet dynamics, but of course that's much more situation specific and much more complex. What about masks? Well, wearing masks such as N95, it filters out 95% of the droplets above 0.3 micrometers are supposed to. So fewer droplets, less chance of infection. It also reduces the velocity of ejection for the person who's wearing the mask. The velocity of ejection is greatly reduced. So the mask can help mitigate airborne spread, but there are many questions. Can masks withstand air expelled at high speed, such as sneezing at 20 meters per second, repeated coughs, long duration of use? Sure, they can filter out most droplets, 95% of them, but can they filter out all the pathogens? Pathogens are not seen at the droplets, and smaller droplets may also carry pathogens. So our main conclusions are that the social distancing norms do not provide adequate protection. Ambient airflow, indoors or outdoors, is likely to play a very strong role in travel and dispersal of droplets. A proper ventilation strategy is very important in indoor transmission of droplets. Larger droplets tend to settle fast, but the surfaces on which they settle, they do present a danger of contamination. Similarly, the smaller droplets can travel larger distances and by orders of magnitude larger time and distance. Here are some further references, and this is not a comprehensive list, but just indicative of what out there is. And I would like to thank you very much and conclude at this stage and open myself for more questions. Thank you.